Yeah, so the second part is based on the midpoint theorem. So we are going to do the midpoint theorem here. So let's understand what the midpoint theorem is. The midpoint theorem says that in a triangle, if there are side AB and AC, right, and E and F are the midpoints, then the line joining the midpoints will be parallel and half of the third side. So E is the midpoint of AB, F is the midpoint of AC. When I join E and F, this line is going to be parallel and half of the third side. So if you look at this triangle ABC, E is the midpoint. So AE and EB are equal. And if you look at this side, ACF is the midpoint. So AF and FC are equal. So as per the theorem, if I join this midpoints, then this line is going to be parallel to BC. And this line EF will be half of BC. So this is the midpoint theorem. So midpoint theorem says that the line joining midpoints of any two sides of a triangle will be parallel and half of the third side. Then we also need to understand the converse of this, because this exercise is based on midpoint theorem and converse of the midpoint theorem. So what is the converse of the theorem? If I take the midpoint of one side of a triangle, right? This is midpoint. And if I'm going to draw a line parallel to the base or parallel to any other side, then it will intersect at the midpoint of the third side. So this is the explanation here. This is the triangle ABC. E is the midpoint. So AE is equal to AB. From the midpoint, if I draw a line EF parallel to BC, then as per the converse of the midpoint theorem, F will also be the midpoint. So from the midpoint, parallel to another side will bisect the third side. That means if AE is equal to EB, and EF is parallel to BC, we need to draw this parallel to this, then we can say that AF equal to FC. So converse of midpoint theorem is used whenever one midpoint is given and a line is drawn parallel to another side, then it will intersect at the midpoint of the third side. So whenever we want to prove that this is a midpoint, we will use converse of midpoint theorem. When two midpoints are already given, then we will use midpoint theorem. So converse and midpoint theorem will be used in this exercise. That is the second exercise. So in the second exercise, the first question, ABCD is a quadrilateral. P, Q, R, and S are midpoints. Now remember, the midpoint theorem is valid only for triangles. So by construction, there is a dotted line AC dividing the quadrilateral into two parts. So if I'm looking at this triangle ABC, first I'm looking at the triangle ABC, then PQ will be parallel to AC and PQ will be half of AC by midpoint theorem. By midpoint theorem, I can say that PQ, because this is a midpoint, this is a midpoint. When I'm joining the midpoints, this will be parallel and half of this. In triangle ADC, similarly, I can say that SR will be parallel to AC and SR is half of AC. Line joining midpoints, SR will be parallel to AC and SR is half of AC. Now, if you look at AC, that is common. So from here, I can say PQ is equal to SR. And we know that two lines parallel to the same line are parallel to each other. So PQ will be equal to SR. Therefore, we can say that PQRS is a parallelogram. So first we had to prove that SR is parallel to AC, SR is half of AC. That is directly by midpoint theorem. PQ and AC are parallel and PQ will be half of AC again by midpoint. If I compare this and this, I'm going to get this result, PQ equal to SR. And of course, the third part, if PQ and SR are equal and PQ and SR are equal, parallel and equal, one pair of opposite side is parallel and equal, so it's a parallelogram. So the first part forms the base of the questions to be followed after this. Okay, now let's see question number 2. ABCD is a rhombus. Now we know that a rhombus is a figure which has got all the four sides equal. Let's assume this is a rhombus. And PQRS are the midpoints. So this is P, Q, R, and S. They are midpoints. Show that the figure that is formed inside is a rectangle. We need to prove that this figure is a rectangle. We need to prove that PQRS is a rectangle. Now, please remember, the first part of the proof will remain same. That means in all these questions, first we need to prove that this is a parallelogram. So what we need to do is follow the same procedure. We are going to join the diagonals. When we join the diagonals, let the intersection point be O. The first part in triangle ABC, PQ. These are line joining midpoints, right? So PQ parallel to AC, PQ is half of AC. If you look at triangle ADC, SR is parallel to AC, SR is half of AC. So PQRS is a parallelogram. So this part is the same. First of all, you need to prove it's a parallelogram. Second part, now after proving it's a parallelogram, you need to prove it's a rectangle. And if I want to prove it's a rectangle, I need to prove that this angle is 90. Any one angle is 90. If one angle is 90 in a parallelogram, all angles are 90. So how to prove it's a 90? We know that this original figure is a rhombus. Diagonals of a rhombus intersect at 90. Diagonals intersect at 90 because it's a rhombus. So I can say that angle AOB is 90. We can say that angle AOB is 90. Now, if I name this MONP, that's a parallelogram. A small parallelogram is formed at the center. Why? Because we know that P and S are midpoints. So PS is parallel to DB, isn't it? P and S are midpoints. So when I join the midpoints, PS is parallel to DB. I know that P and Q are midpoints. So PQ is going to be parallel to AC. So look carefully. We have PS parallel to DB. That means MP and ON are parallel. We have PQ parallel to AC. That means NP and MO are parallel. So the small figure that you see inside becomes a parallelogram. So MONP is a parallelogram. And once we prove it's a parallelogram, we know that opposite angles of a parallelogram are equal. So angle P will be 90. Because we know that angle AOB is 90, angle P will also be 90. And if one angle we prove in a parallelogram 90, then all angles are 90. Therefore, we can say that PQRS is a rectangle. We can say that PQRS is a rectangle. So first is proving of the parallelogram, which is common. Then we said that diagonals intersect at 90. Then we proved MONP is a parallelogram. Once we prove it's a parallelogram, opposite angles of parallelogram are equal. So angle P is 90. If one angle of a parallelogram is 90, all angles are 90. Therefore, PQRS is a rectangle. Let's go to question number 3. ABCD is a rectangle now. So the original figure is a rectangle. So it's the reverse question now. And the PQRS are the midpoints. So we have P, Q, R, and S as the midpoints. Right? In question number 2, the original figure was a rhombus and we had to prove it's a rectangle. Now the original figure is a rectangle and we have to prove that PQRS is a rhombus. So construction, we are going to join AC and DB. The first part is the same as I told you. First, we need to prove PQRS is a parallelogram. So we are going to take triangle ABC. P and Q are midpoints. So PQ parallel to AC. PQ is half of AC. In triangle ADC, S and R are midpoints. SR parallel to AC. SR is half of AC. So PQ and SR are parallel and equal. So it's a parallelogram. So this part is common for question 1, 2, and 3. This part you need to repeat here. Now to prove that it's a rhombus, we need to prove all sides are equal. Because it's already a parallelogram, opposite sides are parallel and equal. So to prove the all sides equal, we will prove adjacent sides equal. For that, the simple trick is, we know that diagonals of a rectangle are equal. Diagonals of a rectangle are equal. So AC will be equal to DB. So half of AC equal to half of DB. Half AC can be replaced with PQ and half DB is replaced with PS. So we get PQ equal to PS. If adjacent sides of a parallelogram are equal, then all sides are equal. Therefore, we can say PQRS is a rhombus. Right? We have proved it's a parallelogram, so opposite sides are equal. And now we have proved that adjacent sides are equal. In a parallelogram, if adjacent sides are equal, then all sides are equal. Therefore, PQRS is a rhombus. Moving on to question number 4. ABCD is a trapezium in which AB and CD are parallel. This is a trapezium, AB and CD are parallel. BD is the diagonal, E is the midpoint. Okay, so DE and E are already given equal. A line through A is drawn through E. Midpoint of AD, a line through E is drawn parallel to AB. So this line EF is parallel to AB as well. So AB and CD are already parallel. And it is given to us in the question that EF is also parallel to AB. So this is going to intersect at F. We need to prove that F is the midpoint of BC. We need to prove that CF equal to FB. To prove CF is equal to FB. So we are going to use converse of midpoint theorem twice here. First, I'm going to take triangle DAB. If I'm going to take triangle DAB, DE and EA are already equal. Okay, this is already midpoint. And we are drawing this line. Let's put this O. So we are drawing this line EO parallel to AB, right? Because it's given that when you're drawing a line through E parallel to AB. So this line EO is parallel to AB. This is both given. Therefore, what can we say? We can say that DO and OB are equal by converse of midpoint theorem. By converse of midpoint theorem, we can say that if this is the midpoint and this line is parallel to this, then O is the midpoint. So I can say that DO equal to OB. Now we go to triangle DCB. Remember, both midpoint theorem and converse of midpoint theorem is valid for triangles. So in triangle DCB, now DO equal to OB we have already proved. We have just proved in the first part. And OF is going to be parallel to CD. The reason is that AB and CD are already parallel given. And EF and AB are parallel. So if you look carefully, AB is common. Therefore, from here, I can say that EF and CD are also parallel. Two lines parallel to the same line are parallel to each other. So AB parallel to CD, EF parallel to AB. So this means that EF will be parallel to CD, right? Two lines parallel to the same line are parallel to each other. So EF is also parallel to AB, CD is also parallel to AB. So EF and CD themselves will be parallel. If EF is parallel to CD, then obviously OF will be parallel to CD. Because if EF and CD are parallel, OF is a part of that line. So OF will be parallel to CD. And if OF is parallel to CD, this is the midpoint. So we can say that F will also be the midpoint. In other words, CF will be equal to FB by converse of midpoint theorem. Then we move on to question number 5. In this question number 5, they have given a parallelogram ABCD. E and F are the midpoints of AB and CD. Question is to prove that AF and EC trisect BD. So trisection means division into 3 equal parts. So the figure was already given to us, ABCD parallelogram. E and F are midpoints. Prove that AF and EC trisect BD. That means we need to prove DP is equal to BQ equal to BQ. We need to prove that these 3 parts are equal. So to prove this, of course, we'll be using the converse of the midpoint theorem. But firstly, we need to prove that this figure that is found here, AECF is a parallelogram. So it is already given that ABCD is a parallelogram, right? So if ABCD is a parallelogram, AE and CF are already parallel because AB and CD are parallel. So AE will be parallel to CF. And we know that AB is equal to CD. Opposite sides of parallelogram are equal. So half AB is equal to half CD. Therefore, we can say that AE equal to CF. So from this we get AE parallel to CF and AE equal to CF. So here we get AECF is a parallelogram. We get AECF is a parallelogram. Now this is important. Why? Because when we are using converse of midpoint theorem, we know that in triangle ABP, if I look at triangle ABP, E is the midpoint given. AE equal to EB, this was given to us. Now, unless we know that this is parallel to this, we cannot say that Q is the midpoint. Therefore, it is important that this has to be proved it's a parallelogram. So E is the midpoint already given, AE equal to EB, and now I can say EQ is parallel to AP from 1. Because we have proved that AECF is a parallelogram, opposite sides of parallelogram are equal. So if this is the midpoint, then this will also be the midpoint. So we are using converse of midpoint theorem here. Without proving this parallelogram, we cannot say this is parallel because nowhere in the question is it given that this is parallel. So converse of midpoint theorem can be used now since we know that this is midpoint and this is parallel because opposite sides of parallelogram are equal. So if AE equal to EB and EQ is parallel to AP, we can say PQ is equal to QB. These two are equal. Now I can repeat this process in triangle DCQ. In triangle DCQ, now DF is equal to FC, that is given to us, and FP is parallel to CQ. DF and FC are equal, already given. FP parallel to CQ from 1, because we know that this is a parallelogram, right? It's a parallelogram, and FP is parallel to CQ. Now, if this is the midpoint and this is parallel to this, because it's a parallelogram, opposite sides are equal, then FP is parallel to CQ. Therefore, I can say that P is the midpoint of DQ. So I can say DP equal to PQ. By the same reason, converse of midpoint theorem. So just look at the second and third. We have already proved PQ equal to QB. And now I've got DP equal to PQ. So from 1 and 2, we can say that DP is equal to PQ equal to BQ. And therefore, we can say that AF and EC trisect BD. Now we have the last question, that is question number 6. ABC is a right triangle at C. ABC is a right triangle at C. So this is a right angle triangle. Right angle at C. So let's put A and B here. This is 90 degrees. A line through the midpoint of AB. So this is the point M, midpoint of AB. So AM and MB are equal. From midpoint of ABM, you are drawing a line parallel to the base BC intersecting AC at D. So if you read the question, you will be able to draw this figure correctly. This is 90. M is the midpoint. From the midpoint, you are drawing this parallel to BC. And now the question is prove that MD is perpendicular. Okay, we need to prove it's perpendicular. We need to prove that D is the midpoint. So we need to prove that AD and DC are equal. And we also have the third part, CM equal to MA of AB. So for the first part, this is easy because AM and MB are already equal given. And already it is given that MD is parallel to BC. And therefore, by converse of midpoint theorem, from the midpoint, if I draw this line parallel, then D will also be the midpoint. So AD equal to DC. This reason we will give by converse of the midpoint theorem. Right? So AM and MB are equal. This is parallel. So D is the midpoint. So now we have got AD and DC equal by first part. Now this angle is already 90. Angle DCB is already given to us as 90. And DM is parallel to BC is also given to us. And therefore, I can say that angle ADM is also 90 because they are corresponding angles. Angle ADM is equal to angle ACB, 90 degrees, corresponding angles. These are corresponding angles, right? When we have parallel lines, this is 90, this will also be 90 because they are corresponding. So ADM, ACB, these are corresponding angles. And if it is 90, we can say that MD is perpendicular to AC. So we've got the second part as well. Third part, CM equal to MA has to be proved equal to half AB. For that, we will take the triangles ADM and triangle CDM and prove them congruent. So AD is equal to CD was proved in 1. We'll make use of that. AD equal to DC. And in the second part, we've proved that this is a perpendicular. So I can number these angles. And let's say this is angle 1 and this is angle 2. So 1 and 2 are equal, right? So 2 and 1 are equal because we have proved that MD is perpendicular to AC. Now, if it is perpendicular, these two angles are 90. So 2 and 1 are equal. And DM is common for both. DM equal to DM common. So this means that triangle ADM is congruent to triangle CDM. Triangle ADM is congruent to triangle CDM. And which condition is this? This is SAS, side angle side. And therefore, we can say that CM equal to MA by CPCT. CM equal to MA CPCT. Now, if you notice, M was already given midpoint of AB. So AM is already half of AB. And now we have proved that CM and AM are same. So we get the required result, CM equal to MA equal to half AB. So that's the result that was asked for us. CM equal to MA is half AB. So all the three parts we have got. This is the first part by converse of midpoint theorem. Second part we did by using corresponding angles. And this is the third part where we prove the triangles congruent. And then in the end, we replaced MA as half AB. CM and MA were equal by CPCT. So we get the required result. So that's the chapter of quadrilaterals.